Okay, pull that up. Hmm. There's a lot of little stuff. Talking about so. Good boy. Hello, hello again. So once the questions are up, we're just going through them again, kind of similar things last time, right? All right, cool. Great, 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 great. Oh, look behind you, dude. Look. I know. Oh, you are such a good. He's such a goal. It's okay. It's okay. They're going to be your friend. Do you want to hold him? Yeah, please. Oh, look at you. Look at that. It's not so bad. Oh, okay. Yes. Yep. Yep. I've had lots of people try to steal him, but his force of attraction to me is too strong via Cam's law. Okay, what do I want to do? Oh, please pet the dog.
Oh, sorry.
He's a good boy.
I love like the smell of like the.
I do too.
What's his name?
This is Bilbo. Okay, that one's interesting. He's got some theater ants who gave him a lot of sweaters as winter was coming, and so now I gotta make sure he's wearing them, especially when I shaved him, and it's a little cold sometimes. It is. It really is. Which part of me loves because I am from Michigan, and there's something about it where it's like, oh, this just feels right for some reason. But
I'm from Jersey. It's actually been colder here than it has been there.
seriously,
Yeah.
oh my gosh.
Yep.
I would love to get. I haven't done enough of the east side of the that coast.
Yep, yep.
Boston is like one of my absolute to
Boston's
dos.
nice. Boston's
I
nice.
just can't wait to see the history of it all and stuff. I just recently did New Orleans, and that is an
Oh yeah.
awesome
I've never been
city.
there.
Oh, I love that city. Such a cool one. You can, yeah. Do you have any dogs?
I do. I have two dogs.
Oh,
They're much
cool.
bigger than
Yeah, he's a little muffin.
Huh? Huh?
Yeah, he's a good boy. He's a good boy. Yeah. Yeah.
Oh.
Go say hi. Look who that is. Over there. This is Bilbo. Also, will you remind me of your name? I know I think I taught you at some point, right? Yeah. It's always like these people I see them, I'm like, oh, they grow up so quickly, you know? Oh, man. Good boy. And I can't memorize names for whatever reason. Oh, sure. Yeah, yeah. Even that makes it a little harder. But I guess I could say that the labs are smaller classes. So in some ways it can make it easier, but. Oh. Okay, 1, 2, 3, 4, 5, and we have 5, 6 will come up soon. Okay, that makes sense. Cool, 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 cool. Oh, man. Hmm. CONH2, the structure you drew. You said it, it makes sense, but yes. 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 All right, guys, we will go ahead and get started. Happy Halloween to everybody. I don't know. This is our spooky LA session. Let's go. So we'll just go through everything, and it looks like it's mostly Lewis structures. For people in other professor sections, have you started to talk at all about MO theory? No? Dang. Or sorry, not MO theory. I'm sorry. Sigma bonds, pi bonds. Okay, awesome. Then we will mostly focus on Lewis structures, but at the end I might, or maybe throughout, I might talk a little bit about how we can start hinting at some stuff because, in my opinion, and maybe you can disagree with me, but after teaching 202 a few times and then 203 and 204 once, I do think orbitals are the most useful thing students are going to take from Chem 150 moving forward. So continuing to remind them that these Lewis structures, as we transition into moving beyond these lines and dots, they're much more than that. They are now these spaces of orbitals that we're taking these S and P orbitals is what we're focusing on, and seeing how they form the new orbitals of sigma, sigma star, pi star, SP, SP2, SP3. So students have to consider 7 new orbitals that likely are completely new to them. And so we want to firm that up because that is principles of reactivity, are those sigma bonds and pi bonds, anti-bonds, et cetera, et cetera, et cetera. So we'll start with 1, and whoever it is, who's my number 1? Peter, let's go. Let's go, Peter. I love chemistry. Yeah, and I think for this one, I guess, does anybody else have any comments before I go into it? Any thoughts about because what's more valuable to me is how are we presenting this to students, and we have two avenues that we can go with. We can present it in a way of a quick way to get answers and get points, which I'm partially okay with, and also deepening understanding for those who want to have a more, what do I want to say, fulfilling experience in 202. Yeah, go ahead.
I think just as kind of like a general rule, the only time that I feel like a lot of students are going to see positive, like anything above one charges on their Lewis structures, is if for some odd reason there's a metal in it.
Okay.
And then that, that's just so rare, even up to like 204. I mean, you might start like maybe if you guys covered grain yards in 204, but or like Suzuki or whatever. But I think that just having that as like if you can have like a single just positive one or minus one charge, that's usually like a good rule. I feel.
Because what you're walking into, I think it's Surhi, or it's taught lots of different ways.
Yeah.
But we need to start, thinking about what are we saying when we say plus one charge, plus two charge. What do these things mean in terms of stability, energy levels for the rest of the molecule? But yeah, I agree. Any other thoughts on this one? Yes, go ahead.
I think it's just really important as they start doing Lewis structures because some might have more practice with this than others, and especially if they come from a high school where like they're just kind of taught like the shorthand, like whatever. Like you have to make sure that they actually understand like what the Lewis structure represents and what it means. So just like honestly taking the time, at least with the first one, to just go through like step by step, like okay, like lay out the atoms, then make sure everything has the octets, then make bonds and erase the lone pairs, and like just to like build like that like kind of step by step like method for them, so that if they do get stuck on a Lewis structure, it's not just like memorization. Like they can go through that step by step and like make sure that they know how to build any Lewis structure. And I think that obviously like you did a very good job in like writing out the number of valence electrons first, and like knowing how to calculate that, and then being able to like make sure that everything fits within that step by step. I think a lot of us learned it kind of that way, where like we fill the octet first and then break the bonds and then label the formal charges. Like make sure that they know that process very well. Especially at the beginnings. I think, Lewis structures are kind of like the rest of this worksheet. So yeah, just make sure that like they have that down. I think is very important at first.
Yeah, and I want to add to that really quickly that what it to me is extra important about going through the steps, and the steps ask them to put the least electronegative atom in the center, other ones on the outside, stack valence electrons on them, and then the really cool thing is they say if you need to move electrons into like a double bond, like we see here, a triple bond. And effectively, what are we teaching them at that point, and they don't even know it? If we target the movement and we use notation to move it, we can use arrows. We can start implying electron pushing arrows already with Lewis structures, and the students won't necessarily need to know it, need to be taught it, but I would recommend showing the whole process, right, of going through that, so they see electrons as not static things, but things that can move, change, evolve, and we can notate how they move.
Yeah, one quick note, one thing that we always say is least electronegative goes in the center, and I think this is a good way to like explain why that is. Electronegative generally means I want my electrons. If you put something in the center and it has to form bonds with other things, then it has to give up some of its electron density to form that bond, so it's a little bit further away from its nucleus. And so that's like, and you can also emphasize like what does it mean when something has a positive charge? That means it's giving up an electron, even though it's like a formal charge, so it's not technically charged. But so I think that's a good way to bring those concepts together.
Yep, I agree. I 100% agree. Anything else? Nope. Okay, awesome. I'm good with that one. Thank you again. Thank you. Oh, there's that one. I'm not even. Let's go to the red 2. Oh, that's 6. I think that's 2 for some reason. Yeah, let's go. And matches too, I'd like to point out the red and the red, but completely on purpose.
Yeah. Okay. So for number 2, it's asking why SF1 forms but OF4 doesn't. And what I put was that it's a reference to how sulfur has the expanded octet. It's in the 3rd period, and so it has the orbitals available to it. Yeah. So it can accommodate more than 8 electrons, and then I thought it was important to draw the Lewis's out.
Yeah, and I think the thing to, again, this is such a good example of why I like going through the steps for the Lewis structures, because I don't want to have the extra 2 electrons that I think are on the oxygen, only because then it's not as easy to explain the other skill, which is formal charge. Yes, we had it over there as well, but just being able to add up that formal charge I think is important. Other thoughts on this example in terms of other things we can bring up? Certainly, well, actually, before I add more, Other thoughts about this one? Then let me add just one more. And this is tricky, I think, but it might be worth on the sulfur one. Put the lone pair it's such bad notation though. What I'm thinking about is I want to get back to the Vesper core shape for this sulfur thing and reminding students that the electrons on sulfur are in an area, but if we draw a bond, it's kind of awkward. So I don't know exactly how I want to notate it. I'm not sure if we have any official notation for it, but I guess the best attempt would be some sort of oval in a way to do this type of trigonal bipyramidal thing. So that would be the only thing I would add to it. And then again, going through the formal charge I think is super, super important. But awesome. Thank you. Number 3, who we got?
Oh, that was me.
Yes, let's go! Let's go! You can explain it there, I don't care, but you deserve applause. Thank you for presenting.
So for this one, it was asking why the bond length of this compound on the bottom is greater than the one on the top. So I just drew the Lewis structures for them, and the idea is that in any resin structure that you draw from the bottom option, you're always going to have a positive charge localized on your nitrogen. So because charges repel, that will lengthen the bond. Whereas on the top one, there's no charges, which is normal.
Yeah, I agree. Any other things people want to add to this question here? Because there's something that I kind of want to bring up in terms of there's more than just single bonds in this. There's double bonds on the bottom one, and we could start talking a little bit about what do I want to say? The O-, we can talk about the tetrahedral orientation of the lone pairs. They are still trying to get as much space away from one another, but that's causing some repulsion on the bond, as well as the double bond is bringing the O's closer to the nitrogen. So yes, it's trigonal planar. That's nice. But as we're bringing it in with the double bond, we're bringing these electron clouds on the outside that are coming in. Another possible thing to kind of have students start visualizing in their head is hydrogen versus oxygen is very different in terms of hybridization stuff. We can ask students, what is hydrogen's electron configuration? It's 1s1. There is no hybridization that it can achieve. So what do they see in their eyes? They see electrons that are primarily a sphere being pulled into nitrogen, and it's the smallest sphere possible. Then we go to oxygen and we say, what's that electron configuration? 1s, 2s, 2p, and it's getting more electrons through its bonds. Isn't that a bigger orbital? Isn't 2 orbitals bigger just by definition? And so we can for our visual students, try to remind them these are clouds, these are objects, these are shapes, they have sizes to them. They have approximated volumes to them is what orbitals are giving us. And tying all the way back to electron configuration is super, super helpful, because every time we can show a student that a skill you learned helps you with reasoning elsewhere, helps you visualize things better, for me was very fulfilling when I was learning chemistry. And again, I'm in both camps of if we just get points, great, but if we're also looking for some other things about this that are interesting, I'm up for that as well. Other comments on this one? Oh, Lewis structures, so wonderful, kind of. Okay, let's go ahead and do 4. Whoa, let's go!
So 4 asks you to draw the Lewis structures of NO2 and Cl4. So I did that here, and
Nice.
I go over the rules and stuff again. And then it asks if you had an H plus, where on these molecules where it would be protonated. And so I said it would be protonated on the oxygens with the negative, because the positive on the hydrogen and the negative on the oxygen will attract. And then I just stuck the hydrogens on these Lewis structures here.
There's something goofy I want to do with this one. Does anybody have any thoughts on this one? Because I'm very interested in, well, I guess it's both of them, but my like fun thought is, for both of these structures, are they really the representation of the molecule in terms of sometimes Lewis structures can't describe a structure because of resonance? So I'm wondering if it's actually a trick question in some ways. Can't we say it can go to any of the oxygens? Or we can imply that we are telling them in class that there are resonance structures where it is a combination of the negative on all four oxygens. So instead of saying, yes, obviously it does go, or not obviously, yes, it goes to the oxygen, that's the correct answer, we'll likely get them lots of points. But this example, you can go further with it with the students and start to bring in the resonance concept of Lewis structures, because they can show I think part of Lewis structures when we teach them is we say look for Lewis, or look for resonance structures. And I would do that in this one. And then it gets back to my thought I had over on this one as well. Can I steal a marker from you? And I think this notation is actually okay, but if we want to do that just to maintain these shapes that they're seeing over and over and over again, trigonal, planar, tetrahedral. And then it's really difficult with this, I think, because how do I show tetrahedral double bonds? I don't think that the notation is particularly accurate, but you can at least remind them that those double bonds, that these are not on the plane.
Yeah.
Something else is different. And if we wanted to imply that, we could say maybe we throw that one back just to imply some three-dimensionality to it. But yeah, I would recommend talking about yes, they're all the same structure, but we can't really say it's one of the O minuses gets it. It's a partial negative on all the O's. Once we fill it, molecule becomes neutral, and then we do have a Lewis structure that represents it. And yes, we'd have to isotopically label the O's to really show, but the theory says it could be any O. All right, moving on to number 5. Let's go!
Okay, so number 5 just asked us to rank these 5 compounds based on their ionic character.
Yeah.
And for the Cl whatever bond, and for the ionic character, it's just the difference in electronegativity between the atoms. So Cl and Cl, they're the same. And then ClBr, they're only a little different. And then CCl4, this carbon and the chlorine, there's a bigger electronegativity difference. And then, yeah, so on.
Yeah, I'm a little. Does anybody know why this question is on this worksheet? What is it trying to achieve on this worksheet? I'm not like setting a trap. I have no idea. I have no idea what it's trying to achieve, because I feel like we've been over this in some ways, and we could even go into more of a Coulomb's law approach to it as well. But
I think the core of it is just like we're talking about forming bonds and forming compounds right now, and we're kind of tying in the previous discussion about periodic trends into this discussion about compounds and how bonds are formed, because I also think it's really easy to, as it is for us, to go from a place like this where we're talking about a fully covalent bond like chlorine, and then talking about an ionic bond like potassium and chlorine together, and how the difference in electronegativity causes that to be a more ionic bond. You can also bring that exact same kind of periodic trend logic into the idea of like polarization within even covalent bonds, or how electronegativity impacts how the electron charges are distributed and things like that. So I think it is just like I did not make this.
No.
My guess is just that we're like going back to the idea of like making compounds and like looking at the periodic trends and how it affects how compounds are made and arranged.
I think it's also good to just like bring in questions from previous modules.
Sure.
Because like they do have a final at the end of the day, and if you didn't understand it last module and didn't do as well on the test, now you can take the opportunity to learn it better and apply it to the newer material you're learning as well. So I kind of like how sometimes the worksheets have other module questions
that look back, but we're still talking about bonds. Yeah.
And also, I think now students are learning about joint covalent bonding, but they always forgot they learned ionic bond before. So I think one example we did in class is like NaOH, and I'll walk around, a lot of people make a bond, draw a line between sodium and an oxygen, because they're confused, like, oh, I'm practicing covalent bond, everything should be line connected, but that's not true. We know from this question there's, due to the huge electronegativity difference, they form ionic bond, which means there will be positive charge and negative charge attracted by the electrostatic attraction. So it's also a really good tie back to what we learned before.
Yeah, I think to that end, then I might suggest bringing back Coulomb's law a little bit into this discussion, or at least saying this is a tool to consider some of these things. And then if we want to expand it further, the force version of Coulomb's law, the force of attraction of a proton on an electron, we may want to highlight that again because what it implies is that is the force that is distorting the orbitals into the new shapes that our students are starting to see. And if they distort them so much, like in KCl, it gets completely distorted where a wave function, an electron, completely moves over the orbital, gets vacuumed over into a new space, into a new orbital, fills a new wave function potentially. And so in some ways we can look backwards and we can look forward while still talking about bonds. My one other thing, again, if you're looking for time in these LA sessions or you're looking for extra help, choose some of these like CCl4, CL2 is maybe too easy, but you could try to do some Lewis structures with these as well and think about the Vesper shape for them, the egg and all that kind of stuff. But awesome. Moving on to 6. Let's go, 6.
Okay, so number 6 just deals with like a lot of Lewis structures, and
Mhm.
being able to kind of draw them, showing the Vesper bond angles, and like understanding the EGG and shape. So yeah, I think for this one it's just important to kind of like reiterate a few things. Like number 1, like when you're drawing the dashing wedge, like it's good notation to like draw them like right next to each other, so making sure that students are kind of following that. And also making sure they understand how like a lone pair relates to bond angle, like not only just like knowing that it'll make the bond angle less than what you would normally expect, but like understanding the reason for that and like more conceptually like why that would be due to like electron repulsion. Yeah, I think those are the main things. For B also, this one maybe might be tricky for them to like understand visually why there's 2 different bond angles, so maybe here's like a good time to have them like build it with their model kit to kind of see like this would be like the 180-degree bond angle between like the 2 BRs in the same plane versus like 90 degrees is like between the different planes. Yeah, I think the model kit would be really helpful for this question.
And sometimes an online model kit because it's going to be accurate, it's rotatable, it's very easy to quickly set up one after the other. It doesn't slow down your process. But other thoughts on this one?
I think exactly what you're talking about with like how the lone pairs like play into how it's like slightly less than that 109.5 or slightly less than that 120 or whatever it is. You can draw a very similar thing like what Dr. Pratt drew here on question 4, where you're kind of showing them that like that orbital where that lone pair is spreads out a lot more because they're not contained to that bond, and so they have like that electron cloud is not as localized, and so it can spread out and cause a lot of that repulsion to make it force its way down. I remember like I think it was Jose actually at LA that worked here before who like showed this to me, and he kind of drew like the lobe that this lone pair was in kind of as like a big like balloon that was like folding these bonds downwards as those lone pairs repelled. Yeah, kind of like how he's about to do.
So we could emphasize it, I think, even more.
Yeah, right. And you can kind of just show how it can like spill kind of into the space where those stray bonds would have been forcing them into that fold. And I think just like that visual helps it stick so much more, or at least it did to me, to just see like, you know, these little pairs have like a possibility to move around, and that's why it forces them to bend in further than you would think. But yeah, exactly, something like that. So that could be helpful just in visualizing. I think it's like a lot easier to visualize a bond than it is to just visualize like what these 2 little dots on your page are doing. But if you can like show them the lobe, I think that's super helpful. Or at least I found it very
Well, it has to be helpful, right? It's
Yeah.
202. It is what's coming next
Yeah.
for them. Is these things.
If we're done with this question, I had another question kind of related.
Yeah. I was gonna add something to this at some point, but it's more of a summary thing about all of this. So go ahead.
Okay. Well, I kind of talked with Dr. McGill about possibly doing a model kit drive. So if any of the LAs are done with their model kits and no longer want to use it, talk to me and you can donate it to me, and then we can give it out to students so that they don't have to like buy model kits. And again, like you don't need to buy a full set, but like you just need a tetrahedron, right? So if anyone is interested, let me know. I know you might use it for orgo, but yeah.
That's a really good idea. And there's also in the atomic classroom, that one over there has a bunch of model kits in the lab, or like when you open up the lab door, up on the wall, there's a couple of them there. Obviously, you gotta return them, but and I don't know how good they are, how complete they are, but
So my question is, the three of you, do you guys think it would be useful, like how much of a model kit do you think people need? Like, so I remember for our orgo classes, it was like we could have one tetrahedron, and like that was helpful for like stereochemistry.
Yeah.
But from y'all's position, what do you think is like the minimum number they really need?
I think they need a little bit more than a tetrahedral,
Yeah.
because they don't, they might need a couple more atoms, at least 6 maybe. Or like maybe just even enough to build like a Newman projection.
Yeah.
Um,
And maybe
so-
throw like a couple hydrogens too.
Yeah. So I guess like the point that Ilse is trying to make is like you don't need the whole kit.
Mhm.
And so if they do want, and this is kind of what I've been saying to like people in my class with Dr. Heaven is like, people are like, okay, like what should we do? What should we buy? You can buy whatever kit you want online. It doesn't matter the kit. It's all like pieces of plastic. But just share it. Like split the cost and split the kit among like 3 or 4 people because you'll never use all those pieces. But yeah, I think just like enough to build a Newman projection would be like what I would say.
Yeah, I like that a lot.
But I mean, everyone's different.
Maybe Newman and chair, and maybe you could support a Newman if you make them have methyls on everything, and you could get to it, but.
Yeah, and they can also like share with each other.
I think having enough to make a chair, because then they'll use it in orgo as well, right?
I think that's like the most we ever would get up to,
Yeah.
is that many, but. That's an interesting idea of like doing a drive and then taking all your model kits and separating them into, like, this is what you need rather than doing like full model kits.
Yeah, I don't think I don't know. I feel like no one ever used every piece of their model kit. Like,
I also know like plenty of non-LA people as well that still have their model kits from like last year too, so.
we can always do something like that.
Yeah, I think this is a really good idea. Thank you guys for setting this up.
Yeah, let me know if you guys are done with your model.
But like, we haven't returned them after this year, like they're little parts so that we reuse them and give them to the next class.
Probably little guarantee that people will return them.
But
Okay.
we can't always ask.
Yeah, we can always
Because
ask,
we
yeah.
put little bins out.
Yeah. Okay, wait, Dr. Pratt, was there another point that you wanted to say on this question?
Yeah, so just one kind of last thing, and again, I'm not gonna say it's like super interesting or important, but at least when I first was studying this material, what kind of was helpful to me. But when I was learning this material, I found for me what worked was I kind of created these generic structures because it reminded me that even when I'm filling in as electrons, which again, the notation is not perfect because we're implying in some ways 4 electrons to a professional, but for me when I was first approaching this topic, it didn't matter whether it was bonded to an atom, whatever was going in those circles, whether it's electrons or atoms, I was still finding the A. I was still finding what electron group geometry am I in. And it's worth pointing out to students that you should assign this first. And then what's really the difficult part of memorization is when you do put in lone pairs, what is the best way to put in the lone pairs in order of the way to minimize the repulsion the best, but give them that reminder that they're general structures or general atoms that are in relation to one another that we're then filling with different things. So other thoughts, comments on anything to help with Vesper theory? How did you learn it? Really good ways to think about it? Any, I don't know, mental things that you remembered about it, but no? Going once? Bilbo? Oh yes, go ahead.
So when I first learned, I didn't understand what trigonal bipyramidal looked
Mhm.
like, and I feel like if they're gonna see it in like a practice problem, because I think there's shapes like that, practice problem, something that we could do is maybe show like a video.
Okay, sure.
I found like a really cool video last year that I could just play really quickly if someone
Yeah.
in the sessions.
Because it took me a while too to see some of this stuff. Because like once you're in this world, you're starting to get to inorganic, and then there's what is it, point groups or something that's called later on, and I like just barf in a good way. But yeah, I do agree that and that's why honestly that's why I like the online model kit so much. It's very very nice to go through it and look at it, but sometimes trying to show them that these names are not coming out of nowhere. It is a trigonal, there's the triangle, pyramid, the three faces, and bi, there's two of them, chain on either side. It's kind of cute, but yeah.
I think like one other thing that I was doing when I was learning this was that I was always asking myself like, what's the way to maximize the angle between each of the atoms or groups?
Absolutely, absolutely. I 100% agree, and it's in the name, and it's like, again, when I first learned this material, you're taking on so much that it can be difficult to take on everything and enjoy everything that's going on. But it is valence shell, which is important because all of these lines and dots we're drawing are valence electrons, so they're the valence things. Electron pairs are the things that are going to repulse the most and change the bond angles. And so it's in the name that if we really understand the name, it is telling us what we're using, what we need to focus on, and what's causing the change. So, other thoughts? This is when I realized I liked chemistry, was when I came across this stuff. And then I almost, well, no, I won't say that. Anything else?
And he still became a math minor.
Yeah! Oh, and that's such a joke that I'm a math minor. I should not have gotten that degree in terms of, I don't know anything about math, but we're getting better, so.
Can I just say something unrelated to chemistry?
Please.
So SNAP benefits are getting cut, so people are not gonna be able to eat. So if you have students in your sessions, please remind them that there are 2 food pantries on campus. I can send more info about that. Also, we're really close to the Decatur food pantry. So yeah, just be aware.
There's one at the AMUC. Where's the other one?
I think it's like near
It's Bread Coffee House.
Yeah,
Is
there's
that
also
the
Bread
one?
Coffee
Yeah,
House
there's
as well.
Red Coffee House. Red Coffee House is awesome. They do free coffee like every day,
Yeah.
Monday to Thursday.
Yeah, they have like a free pantry like 24/7.
I thought that was only on Fridays.
Oh, is it only on Fridays?
Well, I have a few friends that have worked in the pantry in the past. I'm pretty sure it's on Fridays.
Okay.
But
never mind.
I
thank
can
you.
send
That's
you
great. Yeah, please send that information. Just send it in the group.
Yeah.
We'll all have it.
Cool. Other thoughts before we go to anything in general going on, chemistry stuff going on,
It's a Friday night / Saturday morning-ish session, have low attendance, don't know why.
Halloween.
Yeah.
All right, guys, thank you so much. Have a safe Halloween.
Wait, please take treats if you didn't take any treats.
Oh.
With you, do that.
It's really exciting.
Okay, let's leave a quick note. Good boy. Okay. Good boy. I know, I see you. You're so handsome. Yeah, of course. And I maybe will be tapped to do another one. We'll see.
It'll be like next semester.
Oh,
Nothing too, like,
sure.
planned out for this semester.
Uh-huh.
But for next semester, there's gonna be like the same kind of situation.
Oh, cool. Very, very cool.
If you have time to offer it.
I mean, I'd be very interested in doing that.
All right, thank you.
I remember last time, like realistically, I was going to lab, and I was like,
Okay, let's make that nice. Okay.